reason why we are trying to deal about it is about because we want to understand arrhythmias in a much better way. Even now, there are some arrhythmias which we are not able to understand, like atrial fibrillation and some complex arrhythmias as well. So, and I really have a strong belief that we will be able to understand if we have a better understanding on the cellular and molecular level. So, a property of a cardiac cell is due to the depolarization and repolarization cycle which is happening at the level of, I would say, which is determined by the cardiac action potential. So, which I already said it, there are different phases of that, like the phase 0, which is called the rapid depolarization. Then comes the phase 1, characterized by early repolarization. Then comes the phase 2, which is the plateau phase. Okay, plateau phase is characterized by inflow of the calcium and the outflow of the potassium. And then comes the rapid repolarization when the calcium channels will close and the potassium tends to flow out rapidly. And then comes the final phase, which is called as the resting phase, in fact. In the resting phase, as we can see it over here as well, there's active transport through the sodium potassium pump, which starts to restore the potassium to the inside of the cell and sodium to the outside, in fact. Okay, so as I was telling you, so there is a big role of these ionic channels, these electrolytes like the sodium, potassium, and calcium ones, which I was telling you. Um, for example, in the buildup of the electricity which is happening due to the rapid depolarization and repolarizations mediated through the various ionic gates, which is I already explained you about. So there are various factors as well which tend to affect such action potential. So what happens is in these action potentials as well, as I already said, there are different types of ionic channels as well, which tends to have a very high number of sodium channels, which will be having the fast action potential. For example, in the atria, ventricle, and the his Purkinje system. There are similarly also cells with very few or no sodium channels, which will be having. Uday, please mute your microphone. Uday, please mute your microphone. Why you guys are unmuting your microphone? Everyone's microphone should be muted. Okay. Then I was telling you, so then there are also different ion channels, which is like cells with few or in fact no sodium channels, and which will be having the slow action potentials. For example, the SA node or even in the AV node as well. So uh, there are different kinds of pacemaker cells with the action potential as well, which is there in the different regions. They're different in the different regions, as I was telling you. What I mean to say is, so if you will be looking carefully over here, so for example, from the SA node, the AV node, then comes the bundle branch, then the Purkinje cells. So on an overall basis, they all are different. They all are different. It is important, as I would say. What is the reason over here is, if we look carefully, they are slightly different, right? Not too much of different. But the thing is, this small difference is the one which leads to the overall electrocardiographic recording, which we uh, are able to notice in our day to day practice. So, it might look a very simple procedure, but it's not. Okay. So, the surface ECG recording is an overall representation of all the sum of all the electrical activities which is happening in the different parts of our heart. So as I was telling you, if we look carefully, the SA node action potential is of course slightly different. From the atrium it is different. The AV node is different as well. Similarly, those bundle of his or the Purkinje network and the ventricles, of course, is different. So it's about everything coming together and uh, causing the impulse propagation, and finally, the normal conduction tends to happen. And this process is possessed by the specialized heart cells and is called by automaticity, which is the ability to fire and initiate a conduction impulse on their own. And pacemaker cells are mostly found in the SA node, but also found in AV node, Purkinje fibers, twistor terminalis. In fact, at rest, the membrane potential is minus 65 millivolts, but as mentioned, there is a slow leakage of ions into the cells. Thus, sodium slowly leaks into the cells, slowly depolarizing it. Once the membrane potential becomes high enough, for example, reaches the threshold at minus 50 to minus 40 millivolts, the calcium gates will suddenly open, allowing Richa, please mute your microphone. Yeah, Richa, can you
Yes,
please
sir.
please mute your microphone? Why do I have to keep on repeating again and again? Okay, now coming back to the topic. So as I was telling you, so conduction in the heart is the first come, first serve. Means faster firing stimulus wins out. That's the reason the SE node alone initiates the cardiac impulse in the normal heart, and if the SE node fails, the AV node is going to take over. And if that fails, the Purkinje fibers will fail. So to tell you, the SE node rate is almost around 1000 milliseconds to 600 milliseconds. Then similarly, AV node rate is 1500 to 1000 milliseconds. Then comes for the Purkinje cells, which is around 3000 to 1500 milliseconds. Okay, so now coming to the normal conduction system. Dr. Mitles, please thank you for sharing your camera details. Can you please mute your microphone? Gosh. Then I was telling you about the normal conduction system. So what happens is even over here, as I already said it about the different conduction systems. So in this, if you look carefully, one of the important things to notice is um, the right bundle branch tends to pass through the moderator band uh, uh, whenever it is present. And then even in this, what happens is one of the important things which is really important, which we all should understand is the conduction actually begins from the pacemakers of the heart and like the sinus node and travels through the right atrium into the AV node, okay, via the internodal tracts, which is which is located in the anterior, middle, and posterior, and also to the left atrium via the Buckman's bundle. And once the conduction enters the AV node, it slows, allowing the atria to contract and fill the ventricles. Once it is out of the AV node, it tends to enter the His bundle, where the conduction is extremely fast. And then it enters, of course, the common AV node, splitting into the right bundle and the left bundle branches. And left bundle, we all are aware, it further splits into the anterior and the posterior fascicle. And the conduction in the myocardium is relatively slow. Thus, an ectopic stimulus originating from the myocardium itself, in fact, has a wider duration. Okay? So, as I was telling you, so we can see all these different branches very beautifully. Okay? And try to notice the innovation of the Buckman's bundle is into the left atrium, in fact. So some of these things which one is doing in the left atrium, it can affect this interatrial conduction as well. So what about the AV junctional tissue? So there's also posterior nodal extension. Posterior nodal extension is not only responsible for the junctional rhythm, but also is the slow pathway for conduction into the compact AV node. And as such, it plays an important role in the AV node reentry. The slow pathway expresses the NF160, which tends to confirm that the tissue is similar to the compact AV node, and various other factors like the CX45, 40, okay, which is present in the high densities and adjacent bundles and the tissue layers of the triangle of Koch. So, the lack of sodium channels in the AV node may also contribute to the slow conduction. However, it is unlikely to be an important as a connexin expression because a reduction in the sodium conductance can produce only a threefold reduction in the conduction velocity. However, a decrease in the intercellular coupling can result in 100 folds, so almost more than 35 times reduction. In addition, a decrease in the intercellular coupling leads to a paradoxical improvement on the safety of conduction. Yeah, and that is why the position of the leading pacemaker site, for example, the junctional pacemaker site, we all are aware, is in the majority of cases is located not in the compact nodes or nodal his area, but in fact in the area which is posterior to the compact node between the coronary sinus and the tricuspid valve. And it is well known that the leaflet of tricuspid valve have pacemaker activity. However, usually the pacemaker site is located near the coronary sinus. And yes, some studies have shown even the coronary sinus can have rhythmic activity. However, usually the pacemaker site corresponds to the AV node like cells. And during premature stimulation and re-entry, the conduction occurs along the slow pathway and the junctional pacemaker site corresponding to the pathway most often. So that is why it is important to be able to understand. So what is happening is the slowing of the pacemaker activity by the coronary sinus showed if there is a important pacemaker activity as well, and only the nodal like cells expressed, for example in HCN4, we all are aware they are expressed at the junctional pacemaker site, in fact. And that is why it is very, very important for us to be able to understand what is really happening. So, if we look carefully in this diagram, what is happening is there are rightward and leftward posterior extensions of the compact AV node. In fact, the compact part of the AV node with rightward and leftward posterior extension is superimposed on the RAO view of the AV septal junction, and the rightward posterior extension runs in close proximity to the annual attachment of the septal tricuspid valve leaflet. Okay, and in the figure B, when we try to look, so there is a schematic representation of the posterior extension of the compact AV node as encountered in a series of almost like 21 randomly selected hearts. In fact, none had a blunt ending posterior end of the compact node. In fact, one of the cases only showed leftward extension. And the dotted lines over here, which we see it over here, it shows the site of transition between the compact node and the bundle. So why are we trying to have a look? Because a lot of times whenever we are trying to do the ablation procedures and all, especially for these arrhythmias, complications will happen. Complications like if you're trying to do a ablation, there may be AV nodal damage, otherwise AV block can also happen. So how to take care of that? So to understand that, understanding of the anatomy is very, very important. So in this image, which we can see the different the special histology of the AV node. in its posterior extension. So as we said it, the compact AV node is resting on the slope of muscular AV septum. Okay, and here later on, what we see um, close to the opening of the CS os, it shows the leftward and rightward extensions, which is encircled over here. Yeah, and then comes the, as I already said it, so this is now a colored uh, slide. So this is more of a three-dimensional image of the apical area of the triangle of Koch. Triangle of Koch is very important, as I had already said it, especially for the AV and RT, atrioventricular nodal reentry tachycardias. It is very, very important. And we can see the multi-layered morphology of the AV junction. And you can also see a thin layer of um, the transitional cells, the compact AV node, and the loosely coupled deep layer of NH transitional cells. And the AV junctional preparation was paced actually at a with cycle length of like 280 milliseconds and 274 milliseconds, which caused the Wenckebach AV block. Okay, and the bipolar electrograms were recorded from the crista terminalis and the bundle of Fizz. So this is what is the beauty of cellular cardiac electrophysiology. You can see everything. Everything can be demonstrated when we are there on the cellular level, and we can do the optical traces, which tends to represent the superimposition of signals from the septum and distal AV nodal areas. Okay, so the famous triangle of Koch. So this has been mapped using the optical coherence tomography of the AV junction. Yeah. So, and this is taken actually from a rabbit heart. So, still, even now, a lot of experiments are being done on the rabbit heart, pig's heart, uh, and also swan's heart as well. So, this was one of the really early specimens, as you could see. So, when we try to see further in some of the canine and swine heart models, the atrial cells along the AV junction, including the slow pathway region exhibiting the node-like function, potentials are highly sensitive to adenosine, and it is also likely that such perinodal atrial cells, which are very sensitive to adenosine, can be involved also in the genesis of atrial tachycardia, right? So, and as we all know, in all hearts, cells like nodal, like EP properties are found around the mitral and also the tricuspid valve annuli, in fact. And these cells have properties of low resting membrane potentials between minus 5, 55 actually, to minus 65 millivolt, in fact. And, um, and a similar change has been noted from the nodal type action potential to the atrial type action potential, especially at the AV annulus, if microelectrode is driven deep to endocardium. Nodal type action potentials are found closer to the endocardial surface. Yeah, so that is why to be able to understand it is very important. So this is another important figure showing the relationship of the connexon with the pores on a cellular level at the AV junction. So whenever we are trying to see the conduction system in the different areas, as I already said it, it will be different, in fact. So, and of course, uh, actually, whenever we do the 3D mapping, normally we can see the activation sequence which is recorded during the endocardial or inside balloon catheter, for example. And we can notice the activation tends to begin in the high right atrium. Let me see if it can play. No, it doesn't play. So of course the activation will start from the high right atrium at the SC node, then it travels through the internodal tracts. The SC node of the SN node. And finally, now, of course, it is not going to stop over there. It will continue to the septal regions, going through the coronary sinus os as well. RV conduction system, it consists of three main branches of the right bundle and Purkinje system, as we can see it over here. Yeah, the three branches over here are there. So Purkinje fibers is an optical coherence using a optical coherence CT tomography scan. So this is a very beautiful. So EP can be beautiful as well and filled with nice, colorful, bright images. So when we are able to see in this figure is Purkinje fiber network, especially in the RV epicardium of the rabbit heart. You should, you must notice over here is about the direct contact of Purkinje fibers with the myocardium. Yeah, so these are these Purkinje fibers, but they are in direct contact with the myocardium over here. So here the arrows are, there are different arrows, right? Which we can see. So which are pointing to the Purkinje fibers, which are larger than the cardiac muscle fibers. They also appear lighter due to absence of myofibers. The Purkinje fibers transmit the action potential through the heart muscle to the heart apex first, which is faster and more direct than cell to cell conduction. And this also allows for the heart to contract as a whole, beginning the contraction at the heart apex. So never think it like this. The heart contraction starts, at the AC node. If you know, no, contractions actually as a whole, it starts from the cardiac apex. So about the Purkinje fibers as of the heart actually tend to ramify into the mass of ventricular myocardium, which is named after Purkinje, uh, the great uh, scientist, I would say. So what happens is the mass of the ventricular myocardium, which tends to carry those potentials, will be contracting after that. And from the termination, the signal is spread into the myocardium, which I already showed you in the last diagram. Let's not forget, the Purkinje fibers are not nerves. Actually, they are modified strands of cardiac muscle. Let's recall that all muscle tissue is excitable, and this property is the one which is used for carrying the information, and that is what is exactly happening over here. So, what is the secondary function in contractile myocytes has been transmuted into the main role of these not quite muscle cells. The fibers run through the subendothelial connective tissue and are not contractile. They don't generate any force because internally they have only a few disorganized actin and myosin fibrils. Nothing like the very regular area of sarcomeres which was seen in the contractile cells. In fact, Purkinje fibers have a good deal of glycogen in them and they stain very strongly with the PAS reaction, which we see it over here in this slide, right? And they are really prominent in some specimens than the other. For example, the dogs and sheep have larger ones. Sorry. And the Purkinje fibers are larger and less well stained. In fact, this is because of the relatively protein poor cytoplasm. And these fibers are the ones which are modified cardiac muscle cells, which is located in the bundle of his, which is the deepest layer of endocardium. Their structure is specially adapted for the rapid conduction of electrical signals to the apex of the heart. And the Purkinje fibers are long strand of barrel-shaped cells with a few myofibrils arranged peripherally around a clear core of cytoplasm, in fact. And the wide central region of Purkinje's fiber cells is rich in glycogen and mitochondria. In fact, the Purkinje fiber forms gap functions, fascia adherents, and also desmosomes with cardiac muscle cells, but not through the typical intercalated disc that normally link cardiac myocytes. In fact, the fibers extend down the interventricular septum, penetrate into the heart effects, and then branch up the lateral walls of the ventricle. In fact, this arrangement ensures that the Purkinje fibers are able to deliver the impulse of contraction such that the ventricular contractions begin at the apex of the heart and then spread up the lateral wall of the heart, ventricle in fact. As such, the Purkinje fibers form an essential component of the sequence of excitation in heart's contractile system. Okay, so if we look at these beautiful moderator bands in the different areas of the heart, so different views like the RV apical, RV free wall, the septal wall, and they are also present, of course, also in the LV free wall as well. So what happens is the right branch of the His bundle, which is not shown over here, it tends to connect the topmost nodes of the left and right conduction system. In the RV apical view, we can notice how the moderator band contains the conduction system activating the RV free wall and the papillary muscle. In fact, the RV free wall and septal views show the right conduction system consisting of one main bundle with several smaller branches. Okay, and we can also see the bundle of fibers that run alongside the interventricular septum. There's a bundle along the both sides of the septum, one distributing to the RV, one to the LV. The fibers extend down the interventricular septum, penetrate into the heart system. Yeah, and this is the typical reason as well. If we will be able to look carefully about the myocardial activation, see. So this is how it goes. So can we understand what is the possible reason for that? So this is the reason. This is how the contraction actually starts from the apex and then to the lateral wards and then to the other areas which I already said it to you. So about the impulse propagation, if we look carefully, for example, from the normal conduction system versus cell to cell, so what will happen is all the activation in the heart, it does start in the SA node, travels through the atria via the internodal tract, if we already understand that. And if the activation uses a normal conduction system, the activation is extremely fast and there's narrow QRS in fact. However, when conduction is happening via cell to cell, the conduction is abnormal and does not utilize the normal conduction system, such as with a premature ventricular contraction. The cell to cell conduction, in comparison to that using the normal conduction system, is extremely slow. Thus, the resultant QRS will be a wide QRS, okay? And that is what is called as the aberrant beats or aberrancy, meaning not using the normal conduction system. And the ECG is in fact a measure of time. Thus, fast conduction results in narrow complex and slow conduction results in wide complex. Thus, the width of the complex of the ECG tells a little bit about what types of conduction is occurring. In fact, the speed at which an action potential propagates through a region is called the conduction velocity, and it varies in different areas of the heart, and it depends on the diameter of the muscle fiber involved, intensity of local depolarization current, and Also, the current, the faster the conduction, the rate of rise of action potential as well. So, in the myocardial cells, if we can see these arrows are pointing to the intercalated disc. Yeah, if we look carefully over here, yes. And there are also striations and branching cells as well, which is present. So, how does the cell to cell impulse propagation occurs? So, what happens is with the intercalated disc, the cell to cell conduction in cardiac cells occurs through the specialized connectors called the intercalated disc at the end of the cells. And these intercalated discs create physical as well as electrical connections between the cells. And these intercalated discs can be seen in the attached diagram. In fact, the second diagram is a micrograph of a cluster of myocytes and can be rotated as it turns. Let me play. No, I'm sorry, it doesn't play. And as it turns, yeah, we can notice the irregular ends. These discs allow for several connections to other cells, thereby creating redundancy. In fact, the redundancy creates safety by ensuring the impulse can propagate even if some cells to cell connections fail. And that is where comes the role of gap junctions. Okay, the action potentials propagate from cell to cell via gap junctions at the intercalated disc. However, the gap junctions are not located just at the end of cells and are also on the surface of cells as well. This is related to the very intricate three-dimensional packing of cells where individual cells are connected to the neighboring cells in various end-to-end and side-to-side connections. And a normal cardiac cell is on an average connected to more than 10 cells, and at least half are side-to-side connections, in fact. So this has been beautifully stained to help us differentiate about the different gap functions labeled with connections 43, in fact. So these are very important. This was again done in a canine model. In fact, the sarcolemma, the red ones, includes that of the intercalated disc of the adult myocyte, which was labeled with a wheat germ agglutinin. So here we see beautifully about the cell-to-cell impulse propagation, the longitudinal versus the transverse conduction. And as we all are aware, the longitudinal conduction is much faster than the transverse conduction across the long axis of the cells. In fact, this difference in conduction velocity depends upon the orientation of the cluster cells and the complicated 3D connections mentioned in the previous slide, which is called as the anisotropy. We should be able to understand anisotropy a little bit better. Why? Because this is the reason for the difference in conduction speed in anisotropy, that since cardiac action potentials or the cells are long and narrow, in fact, uh, the cells are 6 times the width and they are stacked up side by side. The conduction needs to travel through many times more gap junction connections than it does for the cells lined up end to end. And the speed through the gap junctions with a side to side orientation is the same for those for an end to end orientation as well. So, yeah, so animations always help us understand a bit better, right? So, we already spoke about the different conduction velocities over here. And from this, you can see that conduction is fairly rapid in the atria, but once it enters the AV node and the conduction slows down drastically, allowing the ventricular fill and a complete atrial transport. Once the impulse exits the AV node, the conduction will then become extremely fast through the His or Purkinje system. However, once it leaves that system and propagates only by cell to cell, it becomes much slower. Thus, we can see that an aberrant beat such as a PVC will have slow conduction, resulting in a wide complex and earlier mentioned. So in the activation sequence over here, unlike the 12 lead ECG in which each lead records the global or entire activation of the heart, the intracardiac leads, the catheter recording, which is done during the EP, records only the small local area which are positioned at, thus giving the doctors more information on the timing relative to the various positions of the heart. Thus, the doctors can look, or the physicians or the technicians as well can look at the electrograms, I would say, from the various sites and see if they are recording activation in a normal fashion. For example, the normal sinus rhythm, or maybe out of sequence fashion, for example, which is present in the arrhythmias. And as a review, below normal action sequence, it starts from the SA node, and then we can see the activation sequence is more rounded and it involves the slow sodium channels. Yeah, and the automaticity allowing it to fire on it on, in fact. And the activation then rapidly passes through the right atrium and over to the left atrium via Buckman's bundle and the coronary sinus. This rapid activation, which is influenced by the fast sodium channels, is noted in the action potential with the steep slope during the depolarization phase. And the next activation enters the AV node where it slows down because this is such slow conduction. Neither the surface or intracardiac electrograms can record the activity as it passes through the AV node. And you can see the AV node also has rounded action potential affected by the slow sodium channels. The AV node also has automaticity, but normally loses out to the SA node because earlier I had said you about the the one fires the highest dominates. Yeah. So from the bundle branches, the activation enters the Purkinje fibers, and as you can see on the next page, the Purkinje fibers are in direct contact with the ventricular myocardial cells, and that is the first point of actual ventricular myocardial activation. Last of all the ventricular myocardium is activated from cell to cell, first from the septum, and then the apex, and last of all, the base. This is much slower activation than in the His or Purkinje system. But because of this widespread innervation of the Purkinje fibers, the ventricular myocardium is also activated relatively quickly, as opposed to the slow activation which is happening during a premature ventricular contraction that travels only by cell to cell conduction. So that is why these the specialized catheters are kept at special locations within the heart, which was mentioned in the above. Like so, for example, like the Purkinje networks, the bundle of His, the atria, SA node, AV node, or ventricle, in fact, and then the characteristic mm, like the EGM, I would say, which is unique to that site, can be recorded. Okay. So, are there any questions so far? Yeah.